Welcome to Maths with Bob. Today we're looking at applications of calculus to the physical world, and today we're looking at, in particular, projectile motion. And you can see here I've got an x and y axis drawn up. Now, the vector v, I'll just put here, okay, this is our v. Okay, this is our vector, and it's actually, well, it represents the velocity. Now, the velocity actually has two components, as you can imagine, an x component and a y component. Now, where would they be? Well, okay, if you just project down, straight down here, across here, you then have, if you like, coming up this way, down here, this would be the y component of the velocity, called y dot. Across this way, it would be the x component, x dot. And normally you project it at an angle, alpha. Okay. So let's actually have a quick look. This is y dot across here, obviously. So what is the sine of alpha? Sine of alpha, you can see here, is what? Y dot on v. Okay, that's the magnitude of the velocity. And you can see here that, okay, y dot is equal to v sine alpha. And if you have a look at what the cosine of alpha is, what is the cosine of alpha? You can see that would be just x dot on v. Therefore, x dot is equal to v cos alpha. Now that is, okay, so these are, if you like, the components of the velocity, the initial velocity. So you're projecting something at obviously a certain velocity at a certain angle alpha. Obviously, the bigger the force, the bigger the velocity, and those sorts of things. So v is actually a vector. It has, if you like, a direction or an angle. And obviously, the angle will depend on how far it goes, if you like, the range. Now, there are a couple of things I'd like to just mention here, and that is, what happens if I... let's actually just grab this for vector velocity. Now, what happens if I start... Oops, not that one. This one. If I start actually... this is my velocity vector. Now, if I actually fired it off from the top of a cliff, okay, it basically has no y dot anyway, obviously. Now, a couple of things about it. Okay, you can see here initially it's starting at x is 0, y is 0, but in fact I could actually start it from the top of the cliff somewhere over here, say for instance, and then initially I'm firing it from some value x is 0, y is its particular height, say the top of a mountain. And if I fired it off the top of a mountain, okay, like for instance straight out from the top of a mountain into the water for instance, you can see there won't be any y dot, okay, so the y dot has shrunk to 0, but we do now still have an x dot, okay. So you can see here the only component of vectors, if you like the velocity vector, if I actually fired it directly off the top of a cliff, directly outwards, with no inclination, if you like, is x dot. So there's actually no y dot component. But usually there is actually a y dot component, and try to put this back now, back to these original spots. So you can see here there are lots of different scenarios with the velocity and where you fire it from and the angle. And so we're going to have to look at all this in the equations. Okay, so let's look into the equations. Okay, now how do we examine projectile motion? Well, we normally look at the x and y components to start with. So we normally would basically we'd say, okay, let's break it into two, the x's and the y's, and then we'd have a look at the y. We start with y double dot, which is the second derivative, which is acceleration, obviously, which was the gravity. And then we look at the x double dot, which is the x acceleration, which is 0 in this case. Okay, then we'd integrate back to get to y dot, and with respect to t, is here minus gt plus some constant c1. I'll call that c1. Okay, this is c1 here. And we integrate the x double dot back to x dot, and we'd end up just getting call it c2. Now, okay, the first thing is initially t is equal to 0. The velocity v has x and y components, we can see here. So we can see that with t is equal to 0, c1 should be y dot. So basically we end up getting y dot is equal to what? Minus gt plus the constant, which is actually the y component of the velocity, which is, you can see here, v sine theta. So this pen's playing up a little bit. Okay, sine, actually in this case it's alpha, we'll think of alpha. Okay, now let's have a look at x dot. Well, obviously x dot is just the x component of velocity, which you can see here is v cos alpha, okay, cos alpha. Okay, now we then obviously go back to displacement x and y, the actual, okay, here we go. Alright, so we now integrate one more. We end up getting, okay, what y is equal to minus gt squared over 2 plus vt. Okay, this would be a vt. Okay, obviously we're integrating, so we're just adding the variable. Integration vt sine alpha. Okay, then let's put a plus a c3 here. Now, when we go over here, we'd end up getting that the x, or the x position, if you like, is equal to just vt cos alpha plus another constant c4. Now, you can see here C3 and C4 I've written down the bottom here because basically what our initial position will in fact obviously depend, well, if you like, give these particular constants values. So for instance, if t is equal to 0, x is equal to 0, and y is equal to 0, then both those constants are 0. But you can obviously start not necessarily from the origin. You can start on top of a hill or some other position you can fire projectiles from. And so basically we normally find that these constants C3 and C4 are actually 0 because we normally will be starting our projectile motion from 0. So what I'll do now is I'll just actually rub those out and just have a quick look. Okay, these are now our two equations of motion. One of the great things about projectile motion is now all these equations will govern our motion. Okay, you notice there's no air resistance. We are actually, if you like, simplifying the actual projectile motion quite a lot, really. And but in terms of mathematics, these equations will govern our motion, and we'll be able to solve every single problem just with these equations of motion. Okay. Well, okay, we're now going to look at finding the equation of motion. Okay, now, the first thing is we need to look at eliminating the parameter t, or time, if you like. So the first thing is we know that x is equal to, okay, vt cos alpha. Okay, we know that therefore time must be equal to, okay, x over v cos of alpha. Okay. Now, and we also know that y, you can see here y is equal to what? Minus g on 2 t squared plus vt sine alpha. Now, all we do is we plug in the time, okay, just to, you can see you get minus g on 2. Now, t squared is going to be what? X squared over, now what's that? V squared cos squared alpha plus, okay, what are we going to have here? Vt, so let's go write it as V sine alpha times t. Now t would be just what? X on V cos alpha. Okay. Okay, so let's actually try and simplify a few of these things. You can see here we had a v and a v would cancel, just leaving us with what? This would just leave us with x times sine alpha on cos alpha. Okay, tan alpha. That's not too bad. Okay, now we end up getting what? G on 2, so we end up getting, that's right, minus x squared. So it's going to be an inverted parabola, as you can see here. Now what are we going to multiply this by? Well, there's going to be a g on 2v squared. Okay, it's going to be a g over 2v squared, and then a cos squared alpha. Now, you might remember that 1 on cos squared is sec squared, so we normally would write this equation of motion as, okay, y is equal to minus x squared. I'll just rewrite it like this. G, now there's going to be a factor of g over 2v squared sec squared alpha just plus x tan alpha. Okay, so this is going to be our equation of motion, And you can see here, as you suspected all along, that yes, this is a constant, right? That's a constant there, because G, V, and alpha are all constants. So this is basically just going to be a minus x squared curve, or if you like, an inverted parabola. So we know that the equation of motion is parabolic, basically. Okay, so what else can we find out about this? Well, okay, we know it's a parabola, so let's actually just draw up a flight plan. Okay, here we have a flight plan. Right. Now, okay, lens over here, you can see here some value over here. It starts off here. It actually would have a velocity, initial velocity, v coming up that way, which has an angle of alpha. So that would be v alpha. And as you can imagine, this would be the y, and this is the x. Okay, so we're going to actually try and find the height. Okay, so basically up the top here, okay, let's have a look. What happens up the top there? Well, if we go back and have a look, maybe let's have a look prior to getting to the maximum height. Okay, what happens here? Well, we actually have a little velocity vector going this way. It actually has a bit of y and a bit of x velocities, you can see here. But right at the top, the actual, this one here has actually shrunk to 0. So in fact, how we can narrow down this particular time, okay, this particular time here, the time here would be, in fact, if I just let y dot equal 0. Now when is that? So let's actually just try and find the height. Okay. Or they actually sometimes call the maximum height. Max height. Okay, we know that y dot is equal to 0, okay, at this particular spot. Okay, y dot is equal to 0. Just go back and have a quick look at y dot. Okay, therefore what? gt must equal v sine alpha. Therefore, okay, if you like, t is equal to what? V sine alpha on g. Okay, so this is our time to get to our maximum height. Okay, now how are we going to work out its y position there? Well, if you look across, you can see, here we have a y position in terms of time. Okay, so let's just put it into there. Therefore, in fact, this is going to be our maximum height, so we just can call that y max, if you like. Okay, I'll just write y max. It's going to disappear in a second, but let's actually call that y max. Okay, so y max, okay, is going to equal, now you can see here, minus g on 2. Now time, you can see here is v sine alpha on g all squared, plus vt sine alpha, or v sine alpha times t sine alpha times the t v sine alpha on g. Now you can see that we're going to get a v squared sine squared alpha on g there, and we're going to have to do a bit of simplification. So what happens? How are we going to get this? Well, let's try and simplify this. Okay, we need to rub out okay, so we need to rub out a little bit here. So we're going to try and get our maximum height. We'll just try and simplify this a little bit. Okay, so what is it going to be? Well, y max, which is our maximum height, you can see here is equal to minus g on 2. Now, we're going to get a v squared sine squared alpha all over g squared. Okay, and the other one is just going to be plus a v squared sine squared alpha, supposed to be squared there, v squared sine squared alpha on g. Now, we'll be able to cancel one of the g's in the over here. That g will go, and then we'll get a minus a half of v squared sine squared alpha on, oh sorry, it's actually minus 1 on 2g actually. So let's try and simplify that a bit more. Okay, let's write this out. Okay, so let's keep simplifying. Here we go. Well, we end up getting y max. Okay, is going to be, let's have a look, equal to v squared sine squared alpha. It's going to be a negative, and it's going to be on 2g. Then there's going to be a positive one over here, v squared sine squared alpha just on ordinary g. So let's actually build that up to 2g. Okay, and you can just see here our y max will in fact be equal to what? Okay, just v squared sine squared alpha. Now it's all over 2g. Okay, so that's going to be our y max, our maximum height. Okay, that's going to be up here, so that's going to occur when the y value is actually equal to v squared sine squared alpha all over 2g. So that's going to be our maximum height. Okay, let's actually try and work out the time of flight. We'll try and do that next. Okay, how are we going to find the time of flight? Okay, well, if you just have a look, where do we land? Well, if you have a look, we landed over here, obviously. Okay, that's our flight path. We landed over there. We don't know our x position, okay, which is going to be the range, but we do know that we had landed on the ground again, so our y value actually is equal to 0. And this is what we're going to use to help us. Okay, so let's try that. Okay, so if our y value is in fact 0, we therefore 0, if you like, 0 will equal minus gt squared on 2 plus vt sine alpha. And obviously we can factor out, let's just factor out a t, then we get what, a minus gt on 2 plus v sine alpha, and then we therefore, okay, t is equal to 0, or t, or basically what, minus gt on 2 equals, actually if we put that on the other side, positive v sine alpha, okay. Therefore the time is actually, you can see here, 2v sine alpha on g. Okay, so this is the time of flight, and you might remember this is actually double the time it took to get to the maximum height, actually. Okay, so the next thing is we want to work out how far have we actually landed from the origin. So we need to put that time into the x position, vt cos alpha. So let's actually try and work out our range, if you like. Okay, just think of it like range. So we'll just rub this out and just say, okay, we know that's the time. I'll leave the time there, and we'll plug that into the range, if you like. So the range. Okay, how far do we go from the origin? In this case, is where we started. So the range would be just, as you can see here, x is equal to vt cos alpha, and we now have the time. So the x is equal to, as you like, v cos alpha times the time, which is 2v sine alpha on g. Okay, which is, you can see here, 2v squared sine alpha cos alpha on g. And using our double angle results, you might remember 2 sine alpha cos alpha is actually sine of 2 alpha. So this works out to be what? I just wrote it here, 2v squared sine alpha cos alpha all over g, and we combine the 2 sine alpha cos alpha into the double angle result, and we get the range x is equal to, you can see here, v squared sine of 2 alpha on g. Okay, and this is going to be our range down there. So this is the range. Okay. Now, basically over here, you can see here our x position is, our x spot over here is v squared sine 2 alpha on g. Now, just something while we're on this, how do I maximize my range? Well, I've got to maximize my sine 2 alpha. And as you know, the sine curve oscillates between plus and minus 1, so its maximum value will be 1. Therefore, to get my maximum range, hopefully we can see that I need to basically have 2 alpha is equal to 90 degrees when the sine is actually at its maximum. So alpha would be 45. So obviously this is occurring, max range would occur when, so max range is when alpha is actually 45 degrees. Okay, that maximizes our sine 2 alpha value. Okay, all right. Okay, well this is most of the theory for the projectile motion. We'll now start looking at some problems, but I think I'll leave the problems actually for the next video. Okay, bye for now.